So good morning, Brian. So good morning, Brian. So it's already 8 to 9 minutes late. Because we are not moving properly. So I wait. Let's start. So good morning, Brian. Electron transport system. So it's already 8 to 9 minutes late. Because we are not moving properly. So I wait. Let's start. So good morning, Brian. Electron transport system. So it's already 8 to 9 minutes late. Because we are not moving properly. So I wait. So good morning, Brian. And sorry for the late. It was a technical problem, so it take time to solve. I'm extremely sorry for that. So now it's already 15 minutes late. So let's start without waiting for the other people's. Okay, so they left. We can't do anything. So very good morning, friends. This is Abhijit, and welcome to Unacademy. Okay, so this is a Crack Maharashtra CET course, and you can crack it. by attending the lectures which is held on this platform, uh, morning batch, and you can also attend the evening also. Okay, so the physics, chemistry, mathematics and biology, all subjects are under single roof here inside this uh, course. Okay, so before starting the lecture, it is necessary to introduce myself. This is Abhijit Madkar. I have more than 6 years of experience in biology. I also cracked NET CSR in December 2016 with All India rank 60 in life science. Okay, so you are here on the India's largest platform, the Unacademy. If you want to be a part of Unacademy, if you want to join Unacademy, so it is necessary to have this app inside your mobile or your laptop. So install this app. This app is available on App Store. Okay, so if you want more updates about lectures time and the daily update of lectures, so it is necessary to join this telegram group. This telegram group uh, is only for the daily updates. Here you can have a timing of lecture, then the subject, okay, and the teachers. Okay, so different type of teachers and educators are here on this group. If you want to join this group and you do not have telegram, so first download this telegram app in your mobile, then copy this url, copy this link and paste here inside of the search box of your telegram channel, and you will have a join option here at the bottom of the screen, and you can join this. uh, so after joining, you will have definitely have the daily updates, how many lectures are there and what is the timing of lecture and what is the subject and the topic of the lecture. Okay, so this type of details you will definitely have here. So as per your time, you can attend the different type of lectures with a different educator. Okay, so if you do not subscribe still, please subscribe this channel, the channel, and subscribe this an academy. Why it is necessary? Because this single subscription give you unlimited uh, facilities. Okay, so for example, offline facilities is there, so you can just download the videos and as per your time you can watch them offline. Okay, so doubt solving session is also there. You can talk or interact with your favorite educator if you have a subscription. Okay, so if you ask me about subscription, I will recommend you. If you are in a 11th, please take a subscription of this 2 year. Okay, so the fees of a 2 year is a 24,000. But if you take this subscription with a magic code, this ABHIJIT in a capital, so you will have only 21,600 rupees. If you are in a 12th, okay, I will recommend you take a subscription of 12 month. The fees is 16,500, but this magic code will reduce it to 14,850. Okay, and you already complete it your 12. Okay, so who they complete your 12th and preparing for the CET. So this is a facility available for you. So you can take a subscription of 1 month. The subscription value for 1 month is 3,000, but this magic code in a capital Abhijit will give you only 1,499 rupees. Okay, so this is how you can subscribe us for unlimited use of this platform. Okay, let's start with the electron transport system, guys. Are you there? आहेत का रे सगळे? काय प्रॉब्लेम असेल तर विचारत चला, मला सांगत चला मित्रांनो. तुम्ही सांगणार नाही, मला समजणार नाही. ठीक आहे. Last time we already discussed, guys. First, the glycolysis yesterday. Okay, then Crepe Cycle. Okay, yes. Uh, okay, आहेत. Huh? मी म्हणलं गेले काय की आता. Crepe Cycle, and then it's an electron transport system. Okay, so this is three stages which are conducted, or the which are carried by the cell to synthesize ATPs. Okay, so a cell uh, synthesize ATP by this three type of different stages. Okay, so electron transport system is the last stage where the ATP is synthesized by the process or the reaction which called is uh, oxidative phosphorylation. Okay, so Kunal, it's a respiration chapter. Respiration in the chapter, you will have a knowledge about the how glucose is converted into the 38 ATP, or you can say 36 ATP. Okay, so how it happens. So this type of complete reactions are the part of this chapter. Okay, so this chapter is considered as a biochemistry. Okay, so let's see guys. We already discussed the glycolysis and the Krebs cycle. Okay, now today we are going to discuss about the electron transport system. Still I write here one word, oxidative phosphorylation. Okay, so what is oxidative phosphorylation and why we call it oxidative phosphorylation? We know that when we synthesize ATP, the reaction is like ADP plus PI and then ATP. Okay, so the adding of phosphorus group on this diphosphate is called as phosphorylation. Okay, so what is phosphorylation? Addition of phosphate group. Phosphorylation means addition of a phosphate group. But what is meant by oxidative phosphorylation? Okay, so this is how we are going to discuss today. What is oxidative phosphorylation, how it looks like, and why it happen inside of our cell, and what is the result of this oxidative phosphorylation, and is there any importance of this oxidative phosphorylation in our cell or not. Okay, so this type of discussion we will have today. So oxidative phosphorylation, in oxidative phosphorylation, what is the necessary? The most of free energy released during the oxidation of glucose to CO2 is retained in the form of NADH and APDH2. Let me uh, explain this. Actually, what happened when we see the glycolysis in this process? What happened? The glycolysis is converted into the pyruvic acid. Okay, so pyruvate or pyruvic acid. So in this process, the total, if you see the net, okay, I am not going to discuss the total a result of this process. I am going to discuss only a net product. So net, we have two ATP and two NADH plus EH plus. Okay, so this type of products we will have. Then what happens? This pyruvate is again enter into the Krebs cycle. Okay, so here is your Krebs cycle. Crepe cycle. Okay, so we have here two pyruvates because it's a C3 and it's a C6. And in this pyruvate to Krebs cycle, in this reaction, what happened, guys? There is one more reaction. We call it a link reaction. Here, uh, we can see CO2 is removed with NaDH plus EH plus. Okay, so this is a product again. So now we have multiply by two NaDH here. Why two? Because it's a two copies of two copies of pyruvate. Okay, so again in this process a single pyruvate, okay, I am talking about single pyruvate will give rise to 3 NaDH2, 1 FADH2, okay, and one GTP or ATP. Okay, so it is for one pyruvate. I am not talking about the two pyruvate. You can multiply by two for two pyruvate. Okay, so if you see in this process also there is a removal of two CO2 from single pyruvate. Here is one CO2 and here is one CO2. So removal of total three CO2 is here. So single first is here, second and third. So total three carbon dioxides are removed from the pyruvate, and pyruvate is a three carbon atom compound. So the pyruvate is now vanished. We can say it is completely eliminated from the body in the form of CO2. So this is how this process carried out inside of the cytoplasm. The glycolysis is part of cytoplasm, and then this Krebs cycle is a part of your matrix. Okay, so it is inside of the matrix. So here is your mitochondria. inside and cytoplasm outside. Okay, so this is how this process is continued. But if you see, only one ATP is there in Krebs cycle, and it is also in form of a GTP, and there is only two ATP in a glycolysis. So how can we achieve the target of 36 to 38 ATP from one glucose or from per glucose? So in this process, what happens when we oxidize glucose step by step? The glucose contain more energy when it is phosphorylated. It's unstable and it contain more energy. If we extract total energy in a single stage, it may be a cell will burst. Okay, so to avoid the bursting of a cell, our cell is a very smart. We know that nature is a very smart, and in this process what happen, the cell will extract the energy by step manner, and in that process what happen, in a step by step manner, our energy inside our body is stored in the form of NADH and APDH, except of ATP. Okay, so it is now not stored in the form of ATP, and we want to store it in the form of ATP, and that's why this energy from NADH2 and APDH2 is converted into the form of ATP by the process we call it oxidative phosphorylation. Okay, so this is a oxidative phosphorylation by which the energy from this reducing complexes, these are the reducing bodies, NADH and APDH2. So this reducing power, we call it a reducing power. So this reducing power is converted into the form of ATP. So this is a process of oxidative phosphorylation. So let's say guys, what happened? Most of the free energy, we know that NADH and APDH is a form of energy which is stored and released from the oxidation of glucose. Electron released from NADH and APDH is transferred to O2 and result in a S2O. So let's see, I'm going to repeat now. So this was the overall process, and now what happened? This all NADH and APDH2 going to enter into the oxidative phosphorylation. So what happened when this NADH and APDH donate its electron? This electron is again donated to the oxygen which is taken by breath. Okay, so this oxygen is breathe oxygen. So when you donate this electron to this oxygen is going to convert itself into a H2O. So this is the overall process. H2O is a result of our respiration, and your process of electron transport or the formation of ATP is stopped here. Okay, so this is a final product of your respiration with ATP. Okay, so these are the final two products in our body at the end of at the end of oxidation of glucose. Okay, so in this process electron is not transferred directly to the oxygen, but the series of electron carries present in a IMM. So IMM is I write it here in a very short manner. So IMM means inner membrane of mitochondria. Okay, so IMM is inner membrane of mitochondria. But what happened guys, so this electron is not directly donated toward the oxygen, but it is donated like a series of electron transport chain, and then it is moved toward the oxygen. So it moves like this. Okay, so energy of electron is dropped throughout the process. It is more like jumping from one electron transporter to the second, and second to third, and third to fourth, and then oxygen. So this because of this step by step jumping, the overall, if you see, the overall energy of electron is going to reduced, and the final product is a S2O. Okay, so S2O is a not direct final product, it is indirectly, because what happened, the each and every step is like a jumping of electron from one transporter to the another transporter. Okay, so let's say this electron carries a respiratory enzyme complex. So the these electron carriers, so these carriers which are going to throw electron from one to the another carrier are the respiratory enzyme complexes. The we call it enzyme complexes. Okay, so please keep in mind this word complex. The electron start with a very high energy and gradually lose its energy along the chain. Okay, so for example, let's see this electron when donated by Na and FADS2, that time electron has more energy, and with respect to time, when it jump from one carrier to another carrier to next carrier to next carrier, that time each and every jump will result in reduce the energy of electron, and at the final it is result into the H2O. So the energy is going to decrease with respect to the jumping of electron from one carrier to the another carrier. Okay, so a very important question from me, guys. Why electron is a move in a one direction? Okay, so for example, let's say I'm going to draw here the your chain of electron transport system. So this is, for example, first electron transport. Here is second electron transporter. Here is third electron transporter. Here is fourth electron transporter. Okay, so this NADH will give you complex 1 electron, will give you to the complex 1. This EPDH will give you electron to the complex 2. This is complex 3. This is complex 4. Okay, so here is also another complexes. For example, the fourth complex is again here because the second chain is in this direction. Okay, so why electron moves toward the in this direction and not from here second to sorry, third to again second, and second to one, or second to again third? So why not there is a cyclic process or the reverse process or the to and fro motion in electron? Why it is moving toward the next? So the answer of this question, guys, please keep in mind that this may be the question in your examination, because if you see the affinity of these complexes is increase from first to fourth. Okay, so first to fourth it is going to be a increase, it will not going to a reverse. Okay, so that's why the high affinity of complex toward the electron will automatically absorb this type of electrons inside the electron transport system. So this is how our system work with electron transport system. Let's see what happened. So the complexes, which are four main complexes inside of the electron transport system, the name of these complexes are the first complex, we call it NADH dehydrogenase. Please write it down, guys. It is very important to be a mug up this type of names. Okay, so it should be a mug up by you. Please write it down. सगळ्यांच्या पाठ असले पाहिजे. Complex 1 is a NADH dehydrogenase. Please take a screenshot. A complex 2 is a succinate CoQ reductase. A complex 3 is a cytochrome BC1 complex. And complex 4 is a cytochrome C oxidase. How they looks like? Let's see. For example, this is inner membrane of mitochondria, IMM. Okay, so this is a complex 1. This is a complex 2. This is complex 3. This is complex 4. And this is complex 5. Sometimes we call it a 5. Okay, so this fifth complex is a lollipop shape complex, okay, which is responsible for the generation of ATP from ADP plus PI. Okay, so this lollipop is called as ATPase. This is our fifth complex. It's a fourth, it's a three, it's a two, and first complex. Okay, so this is how we label the complex in 1 2 3 4 manner. Okay, so there are total 4 complexes. Mostly there are few complexes, but we are going to consider four here, and we will study the fifth complex at the end of the slide. Okay, so ATPase in this system I already written here. ATPase, this complex is busy in ATP synthesis, also present in IMM. Okay, so this is the part for this sentence. Okay, so this sentence is only for this part, ATPase. Okay, so ATPase is a enzyme which is involved in the ATP synthesis. Okay, let's see what happened, guys. So in our body, let's say there is chemosmatic theory. Okay, so what is chemosmatic theory? So what happened when, uh, let me explain you here. When the electron from NADH is donated here, NADH plus H plus will donate 2 electron here. APDH also has its own electron. It is also going to donate here. So this electron is directly moved toward the this complex 3, and again the transporter came back to bring this electron. So same for this, it is also moved toward the complex 3. Okay, but when electron is accepted by complex 1, that time what happened, this complex 1 is act as a pump which pump few H plus in the space between two membranes. So this is your outer membrane of mitochondria, and here is a periplasmic space. Okay, so this inside of the periplasmic space, this first complex will pump 4H plus. Okay, same here when third complex takes the electron from the complex 2 or the molecule which is acting as a transport between complex 1 and complex 2 to the complex 3. That time this is also going to emit, or sorry, pump 4H plus inside of the periplasmic space, and finally this electron which is now inside of the complex 4 is donated toward the oxygen, and now oxygen is converted into a S2O. At that point also this last complex will pump 2 electrons. So total, if you see the 1 NADH will give you a pumping of 10 H plus out of the matrix, and if you started from this APDH, so APDH is direct donated its electron toward the complex number 2. So complex number 1 is not in a concentration, and because of that we can remove this 4 H plus from APDH2. So APDH2 results in only pumping of 4 and 2, total 6 H plus. So APDH will pump 6 H plus. So these are the pumps. So what happened, guys? Let's see. For example, this is our mitochondria. Okay, this is inner membrane and this is outer membrane. So because of pumping of H plus out of the membrane will result you the positive, more positive charge at the space between two membrane, and the negative charge or less positive charge inside of the matrix. So if you see, it's a potential difference, my dear friend. What is it? It's a potential difference. So due to this potential difference, what happened, our cell is starting or the sorry, not cell, but this H plus is now starting to enter inside of the uh, matrix. So why? Because here is a diffusion pressure, here is a potential difference. So potential difference, we know that a thermodynamical property of the molecules, they are now moving from high concentration to the low concentration, and because of that the H plus are trying to move inside. Okay, so when this H plus tries to move again at the side of a matrix, that time they will not penetrate this membrane, that is IMM, inner membrane of mitochondria. Why? Because we know that inner membrane of mitochondria is a selectively permeable membrane, and it is not allowed by the membrane to pass this H plus from outer side to inner side. So what happened, let's see, guys, and because of that this H plus will enter through this passage. Okay, this H plus will enter to this passage, and this passage is a part of our ATPase pump, and this ATPase pump will result in the production of ATP from the energy which is distributed from the H plus, which is moving inside of the matrix again because of the potential difference. And this is how the ATPs are synthesized in our body. Okay, so if you see the positive charge, more positive charge at one side, and a less positive charge or more negative charge at another side, so this is called as potential difference. So it is generated because of proton, so we call it proton gradient. Okay, and how it happens, and how it results into the production of ATP was a very difficult to understand. And that time what happened, the Peter Michel was the scientist who came into the focus, and he explained very beautifully how it is happen. And this type of or the theory of Peter Michel, we call it a Chemosmatic theory. It is put by Peter Michel in 1961. Okay, so this was the intelligent scientist who explained the chemosmatic theory. Okay, so what is the chemosmatic theory? Uh, Peter Michel proposed mechanism of chemosmatic coupling to answer the question of energy that drive the synthesis of ATP. Okay, so the question was how ATPs are synthesized inside our body, and what is the input. So to understand the input, it is very difficult to understand because scientists was thinking like there is no any input. So how can this ATPase made ATP without any input? So the process of input or the magic of input is uh, revealed by this Peter Michel in 1961. So he put this beautiful model of the chemosmatic theory. So what the model proposed that, so let's see in this, as per this model, the electron from electron transport drive an active transport system which pump a proton from matrix to the intramembrane space. Let's see what is the meaning of this sentence. For example, this is your intramembrane, sorry, inner membrane of mitochondria, IMM, and this is your outer membrane of mitochondria, OMM. Okay, so I'm going to write here OMM. This is the periplasmic space or the intramembrane space, okay, between two membrane. So let's say this is your complex number 1, complex number 2, complex number 3, complex number 4, and complex number 5 also here. Okay, so this is a lollipop. Okay, so this is how the electron transport system looks like. So what Peter Mitchell says, or the model says, when electron is donated by NADH and APDH to this electron transport system, what happens, guys? This electron is a jump from one molecule to the second molecule to the third transporter to the fourth transporter, and in this process the H plus is actively pumped. Okay, so the energy from this electron, as per the Peter Michel, energy from this electron is used to pump the H plus from matrix to intramembrane space. And here are the H plus, means I'm not going to write here the exact number of H plus now. It just let's say it's just positive one side, and the less positive or the more negative at another side. Okay, so this is how it happen when electron moves from, or electron jumps from one electron carrier to the second, to third to fourth. That time the energy of electron is used to actively pump the H plus. What is meant by active? When you see the transport word after active, so it is considered as the ATP consuming process. Okay, so this active transport is an ATP consuming process. Okay, so let's see, guys, in this process what happened, this H plus is actively pumped outside of the matrix. That means there is a use of energy, and this energy is extracted from the electron. That's why the energy of electron is reduced with respect to the its a movement from one side to the another side. Okay, so guys, let's see the second line. This action this action generate an electrochemical gradient, more H plus at the one side and the uh, less H plus at the another side. So this periplasmic place shows a more H plus and matrix shows a less H plus. Okay, so because of that we call it a electrochemical gradient. Okay, so the proton outside has a thermodynamic tendency of flow back into the matrix so as to equalize the pH. Okay, so the proton has thermodynamic tendency. So what it means? It means this H plus or this proton is now going to enter inside of the matrix because high concentration to low concentration. This movement is from high concentration to low concentration, and obviously this movement is now going to happen. Okay, but this membrane, the inner membrane of mitochondria, it is not too easy to transport by the proton. Okay, so this membrane is selectively permeable. We know that mitochondria is not going to allow this H plus to move inside from anywhere, but mitochondria has a special plan for the H plus to uh, move inside. Okay, so this H plus now going to enter in this complex and will came out from the here. Okay, so let's see guys what happened. This H plus has its own energy, we already know that. So mitochondria is also know that, and this ATP pump is also know that there is energy inside of the H plus, and this electrochemical energy can be used to synthesize the ATP, and when this H plus moves inside from this ATP pump, that time this energy of H plus is used by this complex, and this complex um, convert ADP into the ATP with the help of PI. Okay, so this is how the chemosmatic theory act, or the this is how the chemosmatic theory looks like. So this theory or this model is first proposed by the Peter Mitchell in 1961. uh, when protons started moving back, energy is dissipated, and some of its part is used by a synthesis of used to synthesis of ATP by ATP synthesis. Okay, so this is how ATP is synthesized. Let's see a beautiful structure here which shows the chemosmatic theory by Peter Mitchell. So here are more ions in one side, and they are trying to move inside of the other side. But if you see, there is a membrane which is not going to allow to these ions to penetrate this part, and because of that there is a single transporter which can allow these ions to pass from one side to the another side of a membrane. And if let's think there is a power in this a transporter, and the power is that the energy or the velocity of this molecule, or the mechanical energy of this molecule can be used by this the transporter, and it is converted or shifted into the ATP. Okay, so this is how our ATP works, and it is natural rule. It is a tendency of thermodynamic. We know that when high concentration of ion in one side and low concentration of ion in another side, it will definitely move from high concentration to low concentration. Okay, let's see what happened in mitochondria. In mitochondria, outer membrane of mitochondria is a freely permeable, but inner membrane of mitochondria is a selectively permeable. Okay, so it's difficult to cross, and it's easy to cross. Okay, so with the help of electron energy, that is H plus concentration is altered so that it result in a concentration gradient. We already discussed. With the help of electron energy, that means when electron is moving in a zigzag manner through the electron transport chain, that time the energy of electron is extracted by the complexes or the pumps or the transporter of electron, and they just pump out the H plus into the intramembrane space, and it results in a concentration gradient of H plus. Okay, so protein complex or complexes which are present in a mitochondria, they pump proton, so we call it a proton pumps. Okay, so this electron transporter are also called as a proton pumps. This potential difference is used by ATPase enzyme to generate ATP, and uh, to generate ATP from ADP plus PI. Okay, so this potential difference, which is synthesized, or which is a result of H plus concentration gradient, is used by ATP enzyme or ATP synthase enzyme to generate the ATP from ADP plus PI. मित्रांनो, समजतंय का रे थोडंफार? आता सगळं समजेल इथून पुढे. ओके, इथून पुढे आपल्याला सगळं समजणार आहे, कारण डायग्राम मी उशिरा टाकल्यात, काही गोष्टी थिअरॉटिकलीच समजायला हव्यात म्हणून मी डायग्राम उशिरा टाकल्या होत्या. ठीक आहे, समजतंय का? काही शंका असेल तर सांगा मला, मी परत एकदा एक्सप्लेन करतो. आपल्याला जो हक्काचा पार्ट होता आधीचा, तो लिहून घ्यायचा होता. ठीक आहे, मी शेवटी परत एकदा दाखवेल तुम्हाला गरज पडली तर. आता मला फक्त हे सांगा की तुम्हाला समजतंय का? काय गोंधळ असेल, समजत नसेल तर यू कॅन आस्क मी. ओके, so let's see guys, here the diagram is like this. This is a matrix part. Okay, so this is a matrix part, and this is a periplasmic space or the space between two membrane. Okay, so here is a membrane. Okay, अरे वा, समजतोय तुम्हाला? न्यू टॉपिक तुम्हाला समजतोय हा? लास्ट इयर झालाय, न्यू नाहीये. ओके, 12वीच्या आहात. So let's see, this is our diagram. Okay, so before two slides, what I draw was the completely flipped diagram. Okay, so matrix was below, and membrane or the periplasmic space was the upper part of a diagram. Okay, okay, काय हरकत नाही गौडी. So let's see, here the diagram is opposite. Okay, so when you see it, see like opposite diagram. Okay, so matrix is at the opposite side, I mean at the top of the diagram, and membrane is at the bottom side. Okay, so what happened, how this diagram looks like, let's see, for example, this is our mitochondria. Okay, the mitochondria is beautiful structure, we know that. Okay, so too beautiful that it looks like a battery, and more efficient than a battery. Okay, so let's see what happened. I just zoom this small square. Okay, and it looks like this. Okay, so now you can understand why it is like. Okay, so the matrix is at upper side, and the periplasmic space is at a lower side. Okay, so guys, let's see what happened when NADH and APDH are synthesized in a matrix. So where they synthesize in a Krebs cycle. So here is your Krebs cycle, which is already in a running condition. Okay, and NADH and APDH are synthesized in a Krebs cycle, converted or the sent toward the this electron transport chain. So this is complex one. So the name of complex one, you know that. Please read when where you are already, write it. Okay, I already told you to write it, and please read now. The name of a complex one is NADH reductase or dehydrogenase. Okay, so those who do not write it, please write it. These are the name of complexes. Okay, NADH dehydrogenase, the first complex. Succinate reductase is the second complex. Cytochrome BC1 is the third complex, and cytochrome C oxidase is the last fourth complex. Okay, so these are the complexes. Very good. Dehydrogenase. Okay, so the first complex is NADH dehydrogenase. So this is a NADH dehydrogenase. Okay, we know that when we label the enzyme, or when we in the process of nomenclature of enzyme, there is always consideration the substrate which is carried out the enzyme, or the reaction type of reaction which is carried out the enzyme. So here the name of enzyme is NADH dehydrogenase. That means the first name of enzyme is because of the substrate. So what is substrate? NADH. And dehydrogenase, the second name is always the type of reaction. Okay, so let's see. Pyruvate dehydrogenase. Pyruvate dehydrogenase. Okay. So if you see, this first one is a substrate, and this hydrogenase is a type of reaction. Okay. So when you see the two name system in the nomenclature of enzyme, the first name is always substrate and second name is always a type of reaction. Okay. What effect does a carbon monoxide has on mitochondria? Okay, so what effect does carbon monoxide has on mitochondria? So Mansi, we are going to discuss about the mitochondria and its effect today itself. Okay, so let's concentrate here. I already add this slide. Okay, I already add this slide for your monoxide and the other inhibitors also. Okay, so the what are the inhibitors and how they act on this electron transport chain, we definitely discuss today itself. Okay, so don't worry. So is there anything? No. Okay, so monoxide we will detail it in very detail today. Okay, so don't worry, Mansi. So let's see. Now just concentrate on here. It is very important to understand. So let's see, this NADH dehydrogenase is going to reduce the H plus from here, and what happened, the electron is now in the hand of complex 1. So electron is here. Okay, so this electron is now going to transfer toward the CoQ. So this CoQ is a hydrophobic molecule which is always live inside the hydrophobic part of this plasma membrane, and it will never come out of this plasma membrane. Okay, so the CoQ, we call it a Q cycle. Okay, so this molecule will just move from here to complex 3. It will give the electron to complex 3 and again come empty, and again take an electron from complex 2 and complex 1 and again move toward the complex 3. So this is a cyclic process inside of the membrane. So CoQ is a hydrophobic molecule which is always inside of the membrane or inside of the two leaf plate. Okay, and it will never move out of the membrane. Okay, so what happens when this electron is absorbed by the complex 1, or the when electron is in hand of a complex 1, the energy is in hand of a complex 1. Okay, so complex 1 use a part of that energy and it just pump out a 4H plus out of the matrix. Okay, so the now H plus is moving out of the matrix and electron is moving toward the CoQ. Okay, so at same time APDH is also there. APDH is also going to donate its electron toward the complex 2 and complex 2 to the CoQ. Okay, so what is the name of complex 2? Okay, so I am not going to write here the name of complex 2, but in a next slide I will definitely explain you why complex 2 is necessary. And I already told you in the Krebs cycle, please keep this name in your mind. I will ask you in the electron transport chain. Okay, so why I said that, please keep this name inside of your mind, is the answer you will get in second slide. Okay, so let's see. So this complex 1 is now with the electron. It is pumping a electron, H plus toward the periplasmic space. Complex 2 is also there, and it is also accepting the electron from APDH and donating the electron toward the CoQ. And CoQ is a cyclic molecule which is moving from complex 1 and complex 2 to the complex 3. And because of that, what happened, complex 3 is now having its electron from, which is donated from NADH and APDH2. Okay, so when they are electrons are in the heart of this complex 3, that time what happened, this complex 3 is also pumping a 4H plus outside of the membrane, and again when this complex 3 donate its electron to the complex 4, or the electron is jumped toward the complex 4, that time also there is a pumping of 2H plus, and the remaining energy of electron is donated to the oxygen, and there is H2O as a product of our respiration. So okay, this is how our respiration works, and this is how the electrons are transported from one molecule to the another molecule inside of our body. Okay, so guys, this is a complete process. If you see, now there is a more H plus at the part here. Okay, so here H plus are, the concentration of H plus are very high, and the concentration of H plus here is very low. So it automatically generate the diffusion pressure, and if you see the thermodynamic tendency of a molecule, which will definitely move from this part to the second part, and in this process the a plasma membrane which is not going to allow this part because it is H plus, so it's a polar molecule, and polar molecule will not easily transport throughout the this hydrophobic part, so it requires special transporter, and there is only one transporter, that is ATP synthase. When this H plus is moving through the ATP synthase, the energy inside of the H plus is used by ATP synthase, and it convert itself, or the it rotate with this energy, and convert this ADP plus PI into the ATP. Okay, so this is how the ATPs are synthesized inside of our body. So this is the electron transport chain, a beautiful structure which is completely depending upon the completely depending upon the potential difference or the proton gradient. Okay, so why it is oxidative phosphorylation? Because if you see the total process, the overall process, let's see, I'm going to draw here this NADH, okay, is a product of, so please see at the bottom of a screen, okay, right right side of the screen at the bottom. So your NADH plus H plus, okay, plus O2, I mean half O2, so it will result in a H2O. Okay, so you can see, so this oxidation process, and because of that we call it oxidative phosphorylation, same like a FADS2. Okay, it is the same for FADS2. It is also converted itself into, that is electron is converted into the H2O with the help of oxygen, which is a part of our breathing. Okay, so the overall process is like this. Your glucose is here, which is going to enter into the Krebs cycle uh, through pyruvate and fatty acids, which are converted itself into the acetyl CoA, and then again enter into the Krebs cycle. So protein is also there. Okay, so if there is a protein, it will convert itself into amino acid. Okay, after amino acid, the deamination process is there. Due to deamination process, NH3 is removed and excrete. So what is there? A carbon skeleton. So carbon skeleton of amino acid is converted into acetyl CoA and it will enter into the Krebs cycle. Okay, so this is a Krebs cycle or TCA, tricarboxylic acid cycle. Okay, let's see. I'm going to call it TCA. Okay, so this is a TCA, your TCA cycle. Okay, so see guys, what happened when in this process this different type of molecules are entered. Which are the different type? Glucose, I mean carbohydrate, fatty acid, that is lipid, and amino acid, that is protein. So these three type of molecules are used as a source of energy inside of our body. And now we can see these all three type of molecules are now enter into the tricarboxylic acid cycle by different way. And in this process, what happened? This succinate is going to convert itself into fumarate by the enzyme succinate dehydrogenase. Okay, and this enzyme is your complex 2. Okay, so that's why when we was in the Crepe cycle, or we was busy with the discussion of a Crepe cycle, that time I already told you, please write it down and make a star on this enzyme. I will definitely ask you the question about this enzyme, and this was the question: what is the name of your complex 2? Your complex 2 is actually a part of your Krebs cycle. So this is how the Krebs cycle and the electron transport system are connected by this enzyme. We call it succinate dehydrogenase, and this is a process where your FAD is converted into a FADS2. Okay, so if you see directly inside of the Krebs cycle and the junction of the electron transport system, this process actually FAD to FADS2 is not visible. It is something like a magic where succinate is direct converted into a fumarate with the help of FAD and FADS2, and it will enter into the electron, and H plus will move out of the, or pump from the complex 3, but electron will enter into the Q cycle, and Q cycle will donate this electron to transport 3. Okay, so this is how the total process occurs. Let's say this first complex 1, C1 means complex 1, it is blocked by or inhibited by a retinol. Okay, so retinol is the blocker of first complex. So if first complex is blocked, your NADH is not going to use by your body. Okay guys, are you getting my point? So malonate is there, 3-nitro proponate is there. So 3-nitropropionate and malonate, they are also block this complex number 2. Okay, so this succinate dehydrogenase is blocked by this malonate. Okay, let's see the third one. We also have a few type of inhibitor in next slide, but now see here what happened. This H plus, which are more inside of the two membrane, I mean here is a more H plus inside of this side, and here is a few H plus. Because of that, the pressure is from high concentration to low concentration, and H plus want to move here inside of this low concentration area, and that time they came from this molecule, and the energy from H plus is used by this ATPase molecule, which convert ADP to ATP with the help of Pi, and the energy which is released by the H plus molecule. Okay, so this is how your electron transport system works. Okay, so these are the inhibitors of electron transport system. So rotenone and amytal, uh, rotenone and amytal, these are the two inhibitor of complex 1. Okay, so these are the inhibitors of complex 1 mostly. Is there any activator? For example, A is going to activate B, so that time we denote it like this by arrow. Okay, like this. And when, for example, I want to say A is going to block or inhibit B, so that time I block this line here. Okay, so I'm going to draw like this. So rotenone and amytal are the blocker of complex 1. Okay, and antimycin A is a blocker of complex 3. Okay, so it's not 2, it's a blocker of complex 3. Okay, complex 2 is here, it's a peripheral protein. It is not completely penetrate the membrane. Okay, so it is a only peripheral protein. समजते का मित्रांनो? आहेत का सगळे जागे आहेत का? विशेष म्हणजे का झोपलेत? Okay, so here is two molecule of your interest. One is a cyanide. Most of the time you always ask what actually cyanide does, what actually cyanide does. So what happens when there is a cyanide with our or there is a contact between cyanide and our tissue? Okay, so what happened, this cyanide will just block the transport of H plus or the transport of electron to the oxygen, and this oxygen will not going to convert into a H plus. That means what happened, guys? Let's see. Oxygen is two मध्ये convert होत नाही because of cyanide. That means your oxygen is not going to utilize by your body, and that's why the concentration of electron or the transport system is completely blocked. Because if this electron is not donated by this complex to anyone, this complex is not going to take an electron from cytochrome C, then cytochrome C is not going to take electron from 3, and 3 is not going to take electron from Q, and Q is not going to take electron from 1 and 2 also, and that's why NADH and APDH are there. Most of the reducing power are there inside of cell, but they are useless. Okay, and that's why we die in a fraction of second when we had cyanide in a contact with our tissue. So this is how cyanide works. So azide is there, carbon monoxide is there. So these two molecules are not too much uh, poisonous for our body like a cyanide. Okay, cyanide will block the complete entire structure of complex 4. Okay, so cyanide is related to complex 4, carbon monoxide, and azide is also related to the complex 4. Actinomycin, antimycin A is with a complex 3, and rotenone and amytal is with a complex 1. Okay, so who asked me? Mansi. So this is how the carbon monoxide work with this complex 4. Okay, so the most famous, the interpair of carbon monoxide is with our hemoglobin. Okay, so let's discuss it. We know hemoglobin is also called as alpha 2 and beta 2. Okay, so what is alpha 2? So for example, this is alpha protein. Okay, this is a beta protein. This is again a beta or alpha. Okay, so this is alpha, and this is again a beta protein. Okay, so this is how our hemoglobin looks like. It is made up of the 4 different type of protein, and I am going to draw a blue color spot at the center of the both proteins, I mean 4 protein. Okay, so what is this blue color drop? It's a ferrous. Okay, it's a ferrous which is present in a 4 protein also. Okay, so this one alpha or one beta is made up of the it is a tertiary structure of protein. Okay, it's a tertiary structure of a protein. When this tertiary structure comes together, we know there is a quaternary structure. So our hemoglobin is a quaternary structure which is looks like alpha 2 and beta 2 inside our cell. So what happened, if I zoom this part is looks like this. Okay, so I'm going to explain you what carbon monoxide is going to interfere and where how it interfere. So here is your ferrous group. Okay, here is ferrous, which is held by a different four amino acids. And when I'm going to short it. Okay, so when your oxygen come, your oxygen is going to bind here. Okay, so oxygen is going to bind here on this ferrous. So when oxygen bind, ferrous slightly move toward the down. Okay, so this ferrous will move toward the below part in a system. Okay, so see what happened. This is a site of oxygen binding. Okay, this is a site of oxygen binding, and this site is covered by a protein. Okay, so this is a protein which is at the side of the molecule. Okay, so this is how the protein covers this ferrous and the molecule. Okay, so for example, this is one line. So where the CO2 bind, the CO2 always bind to here. Okay, CO2 binds at the uh, end of the chain. Okay, so CO2 will not interfere and never interfere at the binding side of oxygen. Okay, but your carbon monoxide CO directly bind to a ferrous. Okay, so CO bind here like this. Okay, and this CO binds to the ferrous at the point of oxygen binding site. Okay, so what happen if oxygen is bind at the ferrous, it will automatically remove or the knockout or it is donated toward the tissue. Okay, so as per the requirement, as per the concentration gradient, oxygen can detach from the ferrous. Okay, but here what happen, when CO carbon monoxide is bind to this ferrous, the complex this ferrous to carbon monoxide, this complex is stable. Okay, and it's so stable that this carbon monoxide is not going to leave the its place from the ferrous, and this ferrous is now you can say it is a block by longer time or block for the longer time, and because of that we have the reduced oxygen carrying capacity because of this carbon monoxide. If it's more in an environment, it will block our ferrous or the oxygen binding side, and the oxygen carrying capacity of our body is reduced like anything. Okay, so this is how it is poisonous. आणि म्हणून काय होतं मित्रांनो की for example you are stuck in the tropic where more number of diesel vehicles are there. Okay, so if you are stuck in the city, it doesn't matter, there are more number of petrol and the gas vehicles, so there is a no high concentration of carbon monoxide inside a air. But when you stuck inside the traffic which is on the highway, okay, so where the more cargo like vehicles are there, more trucks and containers are there, so these type of vehicles are mostly diesel vehicles, and in this diesel vehicle there is, we know that there is a more emission of carbon monoxide, and that time you feel like vomiting and the other stuff, the it is a feel like what we call it a subconscious also. Okay, if there is a small child with you, it already omitted. Okay, so why it happen, it is just because of reducing in oxygen carrying capacity because of this carbon monoxide which is interfere with oxygen binding side on the ferrous. Okay, so this is how it works. So the last slide of our electron transport system is ATP synthesis. Okay, so this is a molecule, we call it a lollipop. Okay, so this is a lollipop molecule. Most of the time we said it like a lollipop like molecule. Okay, so it is looks like a lollipop, so you can say a lollipop it. but the name of this molecule is ATP synthase. This is a more correct name, but you can say it ATPase also. Okay, so ATPase is also correct, but this ATP synthase is more correct as compared to the function of this molecule. Okay, so what happened? So now here again diagram is opposite what we saw. Okay, so this is a matrix and this is a periplasmic space. Okay, and H plus is moving from this side to the opposite side, and the energy of H plus is used by this complex. So if I draw this complex from the top view, it looks like this. Okay, here are three binding sites. Okay, one binding site, I'm trying to here, one, two, and three binding site. Okay, so at the first binding site, what happened? ADP plus pi will bind. Okay, so when one H plus is removed from this um, complex, this will rotate itself into the second binding side. At the second binding side, ADP and pi make itself in the form of ATP. So here is a formation of ATP, and at the third binding side, this ATP will reduce itself, remove itself, and the binding side is open again to add ADP plus pi. So this is how this complex move rotate with respect to the movement of H plus, or the energy which is extracted from H plus, and convert ADP plus pi into the ATP. Okay, so this enzyme catalyze ATP synthesis by using the proton motive force. So what is proton motive force? The more proton at the one side and the less proton at the opposite side, we call it a proton motive force. Okay, so structure divided into a two part. One is a F naught component which is inside of a membrane. So this component is going to be, we call it a F naught. Okay, so FO. Okay, most of the time we call it a F naught. Let me change the color. So we call it a naught. Okay, so but this is not naught, it's a O. Okay, O stands for the antibiotic. Okay, I'm not going to write here the name of antibiotic. It's homework. Why it is called as FO? Okay, so it's not झिरो नाही येतो O आहे तो O is the initial of the antibiotic which is going to the block this molecule, and that's why we call it FO. Okay, so please find, this is homework, why it is O. O is initial of which antibiotic, which is, sorry, not antibiotic, but yes, it also acts as antibiotic, and it is a blocker of this FO. Okay, let's say F1 component. F1 component is always hanging inside of the matrix. So from here, the upper part is a F1, and this complex is always hanging inside of the matrix. We call it F1 component. Enzyme contain three binding sites which interconvert between three conformational changes. I already explained this ADP binding, then ATP conversion, and then removal of ATP. So these are the three binding sites. Okay. So let's see what is respiratory question. The respiratory question is a concept in which the two things are takes in a concentration. One is uh, CO2 released divided by O2 consumed. Okay, so what is the ratio of this CO2 release and O2 consume for the different uh, molecules which are used as a energy, or the which is used for the synthesis of energy? So this respiratory quotient, we generally call it RQ. Okay, so it is called as RQ. It's nothing but the CO2 released upon the O2 consumed. So for protein it's a 0.7. Okay, for protein it's a 0.7. For fats it's a 0.9. So fat means lipid, it's a 0.9, and for sugar it's a 1, because we know that 6 CO2 6 CO2 is released by absorbing 6 O2. Okay, so it cancel one by one, and that is a 1. Okay, so this is how the sugar shows 1 as RQ. So please keep in mind that when you did not consume O2 in anaerobic condition, in anaerobic condition, if O2 is not consumed, that means not consumed, it is, that's why it is anaerobic. Okay, so O2 is not consumed. That time what happened, the CO2 release, whatever CO2s are released. Okay, so I am going to take a X here, but O2 is not consumed, so here is a 0, and the answer of this equation is infinity. Okay, so if you see the question in examination, like RQ for the anaerobic respiration, it's infinity, my dear friend. Okay, so keep in mind that for the anaerobic respiration, it's a infinity. Okay, so let's see. Only a few things are there. Okay, so it is magical things inside our body. What is the coupling? So coupling means, guys, couplers are the any a part which is uh, what we call it, which is just uh, joining between the two rotating part. Okay, so it is uh, in a contact with the two different rotating part. That time we call it a coupler. Okay, so the coupling is a process of joining two different parts. Okay, so coupler in uncoupler in ATC, electron transport system. Okay, we know that there is a few uncouplers. Uncoupling agent, oxidation and reduction at a high level but do not permit the ATP synthesis. Okay, that means if, for example, I'm going to draw here in inner membrane. Okay, so there is a more positive charges outside and less positive charges inside. Okay, so guys, what is going to happen now, because of uncoupler is any molecule which is going to connect these two sides, which is below the membrane and which is above the membrane, is going to connected by the uncouplers. Okay, so this type of molecules are called as uncoupler. Okay, so these are the uncouplers. Okay, so uncoupler do not synthesize ATP, but they release H plus. And what happened? H plus already contain its own energy, and lots of energy is stored in the form of this H plus, and it is not going to convert into ATP. That time it is going to convert into a heat. Okay, so these are the heat synthesizing molecules inside our body. When we got an infection and we got a fever, okay, so this fever is a result of this uncoupler. Okay, our muscles activate the uncoupler. So that's why we always check fever at the point where more number of muscles are there. Okay, so we have more number of muscles here at the below of the arm. Okay, our tongue is a muscular, we know that. So our tongue is also used to check the temperature of body. So this is how the muscle cell uh, protect us by increasing the temperature of body from the different type of infections. Okay, so this energy or the heat energy is there because of this uncoupling reactions. Okay, so thermogenin is a family, so this is uncoupler. I can say this is uncoupler from the family of thermogenin protein. So thermogenin is a protein, or it is a family of a protein by which the adipose tissue or the animal which are going to be a phase of hibernation, they can synthesize the energy or the heat to protect themselves from the environment. So this is how our uncoupler used or the works in our body. So the fatty people, okay, so they have more fat in their body. If they want to remove this fat, they eat uncouplers. So because of that, what happened? This uncoupler will lick your concentration gradient in a proton, or you can say proton concentration gradient in your body is a leak because of these uncouplers, and it will result in heat, and there is a more consumption of energy but less consumption of less production of ATP. So the what is the result of uncoupler? More consumption of energy. कोणती energy रे? Proton motive force. Okay, PMF. But low production of ATP. So this is how this system works. Okay. Let's say guys, here is a Pasteur effect, so I'm going to write it in a very short manner. So what is Pasteur effect? So what Pasteur observed, he observed that when yeast is exposed to aerobic condition, uh, their glucose consumption and ethanol production drop. That means when yeast, okay, so here is a yeast in aerobic condition with O2, and here is again same yeast with without O2. Okay, so here is anaerobic condition and here is aerobic condition. So what happened? Yeast is a eukaryotic, so it has a mitochondria. We know that. So when oxygen is there, what happens? This glucose is converted into a pyruvic acid, then a Krebs cycle, and then electron transport chain, and H2O is a product with a 36 ATP. Okay, but when there is absence of O2, what happens? The glucose is directly converted into a pyruvic acid and then pyruvic acid into a ethanol. Okay, and the net profit is only 2 ATP. So here is a 36 or 38 ATP from single glucose, but here is only 2 ATP from a single glucose, and that's why this consume more ATP as compared to the this consume more glucose as compared to the aerobic respiration. And this phenomenon or this observation of a Pasteur, we call it a Pasteur effect. Okay, and due to this effect, what happened, guys? The more production of ethanol in a less time, because each and every glucose is now ends when it convert into a ethanol. Okay, if you provide oxygen to this yeast, it will definitely consume oxygen and synthesize 36 or 38 ATP, and it is going to reduce the production of ethanol. Okay, so the if you require more number of production, more number of ethanol or the more production of ethanol, it is necessary to keep it inside of the anaerobic condition. Okay, so the statement which is considered a Pasteur effect is this yeast consume more glucose when growing anaerobically than aerobically. Okay, so we know why it is. Okay, so this is explanation of the uh, yeast which is going to consume more glucose anaerobically as compared to the aerobically. So Warburg effect. So this is very beautiful effect, my dear friend. So Warburg is a scientist who is observed that most cancer cells exhibit increased glycolysis and use of metabolic pathway for the generation of ATP as a main source for their energy supply. Okay, so the most of the cancer cells is using this glycolysis as a main pathway. Okay, so cancer cell are, we can say completely depend, not completely but most of the part of energy is depending upon the glycolysis only. So this effect is called as Warburg effect. Okay, so Warburg effect means the cancer cell, if you compare the cancer cell and normal cell, so normal cell and cancer cell, okay, so these are the two cells. So cancer cell is completely depending upon the glycolysis for energy, and normal cell can use a different pathway for energy synthesis. Okay, so Crepe cycle is there, electron transport is there. Okay, so different type of pathways are there to synthesize the energy, but cancer cell is completely depending upon the glycolysis. So what is the advantages of this Warburg effect? We can uh, find the cancer cell and we can treat the cancer cell by using the glucose containing radioactive molecules. Okay, so radioactive, if there is a radioactive glucose and if you put it into the blood, so it is more correct that most of the cancer cell will use it as compared to the normal cell. Okay, so normal cell is going to store it, or the most cancer cell are having a contact with this radioactive glucose as compared to the normal cell. Okay, so this is how we can treat the cancer or tumor with the help of Warburg effect. Okay, so guys, if you do not subscribe, please subscribe this channel, uh, YouTube channel. Then a Telegram channel is also there. You can join us on Telegram. And if you like my lecture, please hit on like button. And if you do not subscribe, subscribe Unacademy with this magic code ABHIGIT in a capital. It will give you the 10% discount, or more than 10% in few different plans. Okay, so please subscribe. If you do not have, it will give you unlimited use. Okay, so guys, let's see at the evening at 7 p.m. we are going to discuss about the animal tissues. Okay, so second part here, the muscle cells, then nervous system, this type of cell we are going to discuss with the cardiac uh, tissues also. Okay, this type of cell, this type of tissue we are going to discuss today at the 7 p.m. So guys, be on a time. Okay, so the link of this link of this lecture is available on this group of a Telegram, which is Crack Maharashtra CET. You can find us on Telegram also. Here you will have definitely the link from where you can attend the lecture of 7 p.m. Okay, so have a good time, and thank you for supporting me always. Okay, so thank you very much, guys. We will definitely explore more and more with respect to the time if you support me like this. Thank you very much.